What we're required to do today is electric power stations, generating electrical energy from nuclear power. The second thing that we have to do is decay equations, and then we will move forward towards half-life. Okay, so let's look at the electric power station. How does that work? This will be its diagram. So what happens is that we produce electrical and we produce thermal energy by using uranium, and we know that from the last lesson how to start this nuclear reaction with uranium. We bombard or we introduce neutrons. Just a moment. We introduce neutrons or a neutron at a uranium sample, and that breaks down, releasing three more neutrons, and so on and so forth. The reaction eventually gets very high, or you can say that the rate of reaction increases very exponentially, and eventually it starts producing a lot of energy. So we extract that energy from uranium, that is purely in the form of heat energy or thermal energy. That thermal energy is used to heat up carbon dioxide gas. So carbon dioxide is pumped into the container from one end, and it is received out from the container from the other end. And we use that carbon dioxide to heat up water. And then when the water does get heated up, so water turns into steam. Now, over here, the primary question would be, why do we use carbon dioxide to indirectly heat the water? If we do want water to be heated up, we could have used water directly in the nuclear reactor. The problem is that the nuclear reaction or the radiation coming from the uranium, even if it gets to the carbon dioxide, or even if it does convert or interact with carbon dioxide, the radioactive carbon dioxide is not fatal for human consumption. So even if it does escape to the environment, it's not going to eventually kill us. But if radioactive water emits or gets, of course, because this is steam, it's probably very likely that it's leaking from some point, gradually, slowly. So if radioactive water enters our streams or enters our systems, that would be a problematic condition. We can't allow that, or we won't be able to handle that issue. So what we've done is we heat water indirectly rather than interacting it directly with the uranium. We cause it to heat up, or we allow it to heat up using carbon dioxide. Okay, so once the heating process of the carbon dioxide is done, eventually water converts into steam. That steam can be provided to the turbines, and those turbines are then connected to AC generators. The same procedure, if you go towards work power energy, you will find it over there. The same idea, the same procedure, right? So the eventual goal is to convert everything into steam. Whatever apparatus we have to produce electrical energy, we convert everything into heat and try to convert that heat into thermal energy for steam production. And that steam production, or the produced steam, is fed into turbines, high pressurized fan blades. Then they turn or rotate because they are being exposed to steam. And then that is used to generate AC electricity. Anyways, so a few things over here. We have moderators and control rods in this apparatus. You see, when the reaction actually does start, how do we know that when we're going to stop it? How do we know where to stop this reaction and how to moderate this reaction? Because if we let this happen uncontrollably, this eventually does become an atomic bomb, right? And we can't allow that happening at this place. So what's going to happen is that we introduce moderator rods, right? And what do they do? These are primarily made out of boron and sometimes made out of graphite. You see, boron is a good absorber of neutron. It's a good neutron absorber, and it does not become radioactive in the process, which means that it's not going to disintegrate to become something else. So what we do is we introduce boron in the system, which absorbs neutron. So this boron rod or the control rods or the moderators actually absorb neutrons. And if they do absorb neutrons, what's going to happen is that, for example, if previously there were three neutrons coming out of the sample, let's say two of them are absorbed. Now only one of them strikes the next uranium atom, only producing three neutrons. Again, if those two neutrons are absorbed by boron, only one of them may eventually hit the next uranium sample and eventually so on and so forth. Right? So that is how we're going to control the rate of reaction or the speed of reaction of this nuclear power plant. If all the boron rods or control rods or moderator rods are taken out of the system, the reaction will happen uncontrollably. So, depending upon the output requirement of the power plant, if I need more power, I will take out maximum number of control rods so that the nuclear reaction can take place at maximum speed, at maximum capacity, producing maximum thermal energy, then eventually producing maximum electrical energy. So if my requirement from the power plant is low with the passage of time, let's say it's a low power requirement season. For example, in winters, we don't need as much power as we do in summers. So in winters, what we do is we introduce these control rods back into the system so that the speed of reaction will slow down because we don't need so much power. And why do we need to slow it down? Because we don't need that much power. So we will slow it down by using boron control rods or moderator rods, right? Okay, so that is how a power plant would work. And we did discuss nuclear fusion last time, that it is actually the combination of two smaller nuclei to become one larger nuclei. And we did study the term that was mass defect, which was E equals to mc squared. So, and fusion, be mindful that's only happening at the sun, or you can say it's only happening on the stars, and hydrogen is actually our fuel, and helium is our product. And this E actually tells us about the energy. There is a lot of energy even in the single process. It's very difficult to actually carry out this reaction. Why? Because combining two nucleuses together, which have same charges on them, requires a lot of thermal energy and a lot of pressure and a lot of gravitational pull that eventually does cause these nucleuses to fuse together to become helium. So going back, we have looked at the electropower station nuclear power plant, how it works. We have also reviewed how fusion works. Now we're going to work out towards the decay equations. So we have three types of radiations. We have alpha, we have beta, and we have gamma. And for these, we have nuclide notations. So nuclide notation is what you may have done in chemistry already. So nuclide notation actually is just a way of writing down the particle that we're talking about or the atom that we're talking about. For example, if I take the example of sodium, sodium is Na. The chemical symbol for that is Na. And we see two numbers written down in the periodic table. The one of them is going to be 23 and the other one is 11. What do these two numbers represent? So this lower one represents the number of protons only. The upper number represents the number of protons plus the number of neutrons. So if I were to find out the number of protons, neutrons, and electrons, I could do that very easily just by looking at these numbers. So protons will be 11. Electrons will also be 11 if the particle is neutral. For example, it has no charge. So that would mean that protons or the positive charges are equal in terms of electrons. That would be negative charges. But neutrons have to be found out by subtracting these two numbers. So this will be 23 minus 11. That will give me 12 neutrons, right? So this notation that we've written down for sodium, that is 23Na11, this is basically known as nuclide notation. This is what you've done in chemistry. So the nuclide notation for alpha, beta, and gamma, we are familiar with that. That is 4, 2, 0, minus 1, and 0, 0. These are the nuclide notation for the radiations, and we have the particles, protons, neutrons, electrons themselves. So neutron has 1, 0, proton has 1, 1, and an electron or beta, which is primarily the same thing, 0, minus 1. So let's move ahead with decay equations in terms of their application, that if there was alpha decay, what would it look like? If there was beta, if there was gamma decay, what would that look like? For the sake of understanding, what I'm doing right now is I will be taking same atom for all three examples so that we can understand and develop at least one relationship between them. So first we're going to talk about alpha decay, and we know that alpha is 4, 2. So the element that I'm keeping constant across the board, that is uranium 235 92. So I know that the protons, neutrons, and electrons in this neutral atom would be 92 protons because that is mentioned at the lower part, and 235 minus 92. I would recommend taking out the calculator and solving group. That would be approximately 140 something. Let's just verify this. So 235 minus 92, that should be 143. It has 143 neutrons and 92 electrons. Protons and electrons are going to be the same if they are, or if the charge overall is neutral. So uranium disintegrates or decays to become something new. Let's say an element X. We don't know what that is, and it's not a part of your course to remember what it's going to make. So I don't know what the upper value or the lower value is going to be. By the way, the upper value is known as the mass number or the nucleon number. Sorry, not the mass number. Nucleon number, right? And the lower number is known as proton number or atomic number. And this one is mass number and nucleon number. And this is represented as A and this is represented as Z. Again, these are things that you must have already done in chemistry. Okay, so we don't know what these values will be, but I do know about alpha because if I know that it has released alpha, then it will also have released some energy. And this energy primarily is in the form of kinetic energy of alpha and some thermal energy as heat. So two energies that we must mention in P2 question if he asks you. Now, how to find out these values for X, the new element? We don't know what that is. The idea behind this logic would be that charge is conserved. Charge and particles are conserved. When we say conserved, that would mean that the number of particles in a system will remain the same. It's not possible that at the beginning of this reaction, or the beginning of this decay process, we had 92 protons and at the end of it, we may have 85 or 86 or something less or something more. That's not going to happen. So based on this idea, we will develop two equations. Now, the first equation, I'm going to color code this example so that we can remember this later. I will make one equation for the upper part of the system with the green color. Let's make that equation. So 235, the arrow will be treated as an equal sign, and the x is what I don't know, plus 4 that comes from alpha. Again, this is the 4, this is what we don't know, this is unknown, and this is 235 actually coming from. The other equation that I will make is going to be from the lower part, and I'm going to do that with a red color. So the lower part equation is going to be this way. So that would be 92 equals to x. I'm using x again because this is the unknown part, plus 2. And 2 is coming from alpha, right? So let's find out x in this place. That is going to be 90. And over here, it's going to be x equals to 231. Let's replace them back into the system. So this is 231 on the upper part, and on the lower one, this is going to be 90. Now, luckily, what you do, just to verify, if you add 231 with 4, if you add them two together, if you add these two together, you're going to get this one, 235, back again. Similarly, if you add 90 with 2, you will get 92 back again. This is what we mean by that the charges and particles are conserved in a nuclear decay process. And this is going to be true for any type of decay involving alpha decay. For example, let's apply another equation. Let's say that we have an element Y. We don't know what that is, but for the sake of understanding, let's say it's Y. So let's say it has 85 mass number, and let's say it has 20 proton numbers. So 20 protons and 20 proton numbers. So this decays to become something new, let's say a particle W. We don't know what that is, but the examiner has mentioned that this undergoes alpha decay. So I know that alpha is 4, 2. I'm ignoring the energy part of this equation because we want to find out the values first and then we can mention that later. So I know that over here that would be something 4 less. So 85 minus 4 would give me this answer. If you want to go through that equation process, it's your choice. So according to my understanding, this should be 81. The equation that actually gets us this point would be 85 equals to, let's write down W so that we don't forget that. So W plus 4. This will get you 81. This is the equation process that we did in the previous understanding. On the other hand, we have to mention the proton number for the W, the new particle as well. So according to me, this should be 18 as 20 loses 2 because alpha has taken away this 2 and we are only left with 18. But for the sake of understanding, let's make the equation again. So 20 equals to W plus 2. So this will give you W as 18. So this is how the alpha decay equation would work. This is how you calculate them. And if the examiner has left another empty blank on the end of that, then you'll have to mention energy. If he asks you in terms of theory that what this energy constitutes of, then there are 2 points. Kinetic energy of the released particle, that is alpha, and the thermal energy that actually comes from this nuclear process that we eventually do use to produce electrical energy. So they do produce thermal energy. We can access it and we can use it. So 2 things on the output. So this is for the alpha decay. Let's move towards beta decay. And for beta, we must remember that this is what beta looks like. 0 minus 1. So I'm going to take this genetic example again. So first we did alpha decay. Now we're going to look at beta decay. So beta is 0 minus 1, right? And it is similar to an electron. The nature of beta particles is that it's similar to an electron. I'm going to take the same particle, that is uranium-235, 92, becoming something new, let's say particle A, I don't know what that is, plus the beta particle that has been emitted, which is 0 beta minus 1. And again, plus energy, which is again the energy or the kinetic energy of beta, point number 1. Point number 2, thermal energy from this reaction in terms of heat, simply heat. So I need to figure out the values over here. And mind you, that examiner may not give it the values of beta as well. He may miss out these values for you to be filled later. So memorize all of these values. Okay, so since beta has 0 on the upper side, there will be no subtraction and I will get 235 as it is. You want to make the equation, it makes no difference, you will get the same answer. But on the lower side, it's somewhat a bit different. You see, let's make an equation for that. Sometimes students do this in a hurry and find or get the wrong answer. So this will be 92 equals to A plus minus 1 because minus 1 is coming from beta. This place is missing and this is the 92 that we're getting from. So A will come out as 93. Be very careful. This is going to be 93. Although this negative 1 may give you the illusion that you may quickly write down 91 as an impulse. Please don't do that. Only in the case of beta, the number actually adds from 92 to 93. There is plus 1. But why is it happening that way? Let's explore the reason for that. The reason for the Z plus 1 idea. Why is it Z plus 1? Because this number or this number is represented by Z and this one is represented by A. The one that we've done for the chemistry's idea previously over here for the nuclide notation. Yep. Over here. Yes, this is A and Z. Exactly picked out from chemistry. Okay, so why is that so? You should also know that. Why is it Z plus 1? Because what's happening inside the nucleus, the uranium nucleus, where did we get the beta particle from? Because we're not interested in the electron shells in the nuclear reaction. We are interested what's happening inside the nucleus, right? So what we explored or discovered is that one neutron, that is 1, 0, actually breaks down to become one proton, that is 1, 1, and it also releases an electron or a beta particle. So neutron breaks down to become a proton and an electron. But what is the fate of these particles? What happens with them? So neutron got disintegrated, so it's no more there. Proton stays inside. It stays inside the nucleus, and the electron gets emitted out. So that eventually came to be known as beta decay. And now we see why 92 actually becomes 93, because the number of protons have increased by 1. There is a new proton in the system because one neutron got disintegrated. Now let's try to analyze the number of particles inside U and inside A. So this is U, 235, 92, and this is A as 235, 93. Let's analyze, do we see that addition of one proton or not? So protons, neutrons, let's only limit ourselves to that because we're not interested in the electrons right now. So this is 92, this is 93. But let's look at the number of neutrons. What happened with them? So 235 minus 92 gives me 143. But over here, I see 235 minus 93, that gives me 142. I can see this very clearly over here that one of the neutrons is being reduced. So I'm reducing one electron, one neutron. I'm experiencing a loss of neutron, a disintegration of neutron into a proton. So I see that one neutron is less, 143 to 142, but I also see that one proton has increased in number, which means, effectively speaking, a neutron converts into a proton. That is why the number of total particles remain 235. They don't change because if there were 143 neutrons, now there are 142 neutrons. If there was 92 protons, now there are 93. So the addition sum remains the same. That is why beta does not affect the upper value, because what has happened is that just one neutron converted into a proton, the total number of particles are still the same. Because the upper value, that is 235, is actually a representation of protons plus neutrons. So it makes no difference mathematically that one particle was taken out of neutron and was added into protons. It's as simple as saying that reduce neutron by 1 and increase proton by 1. So the overall effect remains the same because the value 235 is a representation of addition of both values, right? So this is my beta decay and the background reason for that. Let's take out another random example. For example, thus we have a particle P, a radioactive element. Let's say it has 145 atomic number, and let's say this is 85. It decays to become something new. Let's say uh, a particle X, right? So, and we know that this is beta decay, so the examiner has missed all of these blanks. You have to fill them out yourself. So what we're going to do, we know from memory that we've memorized that beta is 0 minus 1. The upper value stays unaffected for beta, that is 145, but the lower value is going to be added by 1. So this is going to become 86. And if you still don't get the answer or don't get the procedure, do not rush it or do not panic. I would recommend making an equation for the lower part because the upper part has a 0. We don't need to make an equation for that. It's straightforward. But for the lower part, what you can do is 85. From here, the arrow gives you the equal sign. This one will be the missing value, that is x from the lower part, plus, because charge conservation or charge addition or simply counting the total number of charges would require that there should be a positive sign here. And then simply writing down the charge of the beta particle. So here it's negative. So if we perform simple mathematical algebra, that would be x minus 1. If you take that over there, this is going to become x equals to 86. So whatever logic suits you, either you can remember directly plus 1 addition or either you require this equation to be formed. It's totally your choice. So last we are left with gamma radiation or gamma decay. So we know that gamma has this symbol with 00. We're familiar with that. And to start with the uranium 235 and 92, if it releases gamma radiation, it makes no difference to the particle. The particle remains the same, but it has a lower energy content. It is becoming more stable with the passage of time by releasing gamma radiation. Similarly, if we had, let's say, any other element, let's say an element T, and it has 147 mass number, and let's say this is 87 proton number. So if it is decaying by gamma radiation, it will still end up being the same element because gamma has no charge, no mass. It's not going to take away any changes or not introduce any changes in the atomic structure. Rather, it's only going to lower the energy content of this system. So this question generally is not asked because the question is pretty straightforward and there's nothing to be asked on this topic. So this is the decay equations, right?